bringing implicits to OCaml.
So yes, I'm going to talk about some work that I did before. An extension to OCaml to support ad hoc polymorphism. So ad hoc polymorphism is when you have a function defined over several different types that acts in a different way for each of those types. Classic examples are a plus operator that works on integers and floats, or a print function that prints values based on their type. So a number of languages have support for ad hoc polymorphism. Perhaps we can borrow something from them. The most well-known to this audience, I suspect, is type classes in Haskell. So for those who aren't familiar with Haskell, we have a example here. So this is we're defining a type class show, and then an instance for int, and an instance for float, which describes how to show an int and how to show a float. And what this gives us is essentially it's a function show. It's defined over ints and floats and behaves appropriately for each of them. So a property of type classes which is important to bear in mind is what's called coherence. So what that means is that for each pair of a type class and a type, you can only have one instance in your whole program. And so yeah, if you try and, for instance, declare another instance for show int, we get this error message saying it's not to. And type classes kind of rely on this. So because what it means is that it doesn't matter how they go about finding a show int instance and where they get it from, it's definitely the right one because it's the only one. So that simplifies some of that stuff. But in the MLs, in OCaml in particular, we have the ability to abstract type equalities. So that means I can create a type t like I do here, and then it's equal to int, but then I can hide the fact that it's equal to int and just expose it as an abstract type. And that makes it very difficult to maintain coherence. If you're allowed to hide equalities and things, it's hard to know when two instances are really overlapping, when they're defining on the same time. So if you can imagine, if you imagine that we've added type classes to OCaml, it might look something like this. In this example here, we've got this functor, and it's defining an instance for show on x.t, where x isn't a parameter. And then we define an instance for show int, and then we call the functor f with type t equals int. And here, we're clearly defining two instances of show int, but there's nowhere in the program where, without breaking abstraction, you can see that that's what's happening. So it's things like this that make it difficult to try and put type classes directly into OCaml. So can't use type classes. Where else can we look? Well, as we just saw, Scala has implicits. Just over-explain again. So what they give you the ability, so they have implicit parameters, and what I let you do is have a parameter to a function that is selected from the scope of the use side of the function based on its type. And this is essentially the same example we showed for Haskell, but in Scala, hopefully correct. So what we're defining as type showable, and then we're defining this show function, which is takes an implicit argument s of type showable t, when t is the type of the other argument, and then calls the show method from the showable argument. And we can define this implicit object, int showable, to have show ints. And then when we call show on an integer, it looks up the scope, it sees this int showable, and it passes that as the argument s for show. Yes, so it's important to note that implicits don't have this coherence property. Here you can define two objects, mark them both as implicit, even though they have the same type. So here we've defined another way of having int showable, another way to show ints. And there's no error on the definition of that. However, if you try and use show on an integer after that, you'll get this error saying that it's ambiguous. It's looked up, it's seen two showable int objects, int showable and int showable 2, and it doesn't know which one to choose, so you get this error message here. So that's promising, so let's try and convert that across and use it in OCaml. So the idea is essentially to have implicit module parameters to functions which are chosen by their module type. The module type. So yes, and so how that looks in the system that we have in modular implicits is you define yourself a module type show with a type t and a value from t to string, and then we can define this show function which takes an implicit module parameter s of module type show, and another argument x, and applies s's show value to x. And so the type of show is written like this. We've got implicit s of type show, and it goes to s.t to string. And so how show is going to work is when you apply it, we're going to look up in the scope to try and find something that we can use as our argument s, so something in module type show. We don't really want to be able to just use anything, so we've got to have a way of identifying the modules that are intended for this kind of selection as an implicit parameter. So we have that, we just annotate module definitions with this implicit keyword. So here we've got a show int and a show float, telling us how to show either of those, and yeah, they're marked implicit, so they're available for selection. So with these definitions in scope, we can now call show on integers, and we can call it on floats, and it does the right thing, ad hoc polymorphism and everything, which is good. Yes, so the other thing that's available for selection is other implicit parameters. So in this print definition at the top here, we've got this implicit argument s, and that's going to be used itself as the implicit parameter to show, the call to show on the second line there. So this is another thing that's different between type classes and implicits. So in type classes, you'd write something more like the second definition, and Haskell would infer the need for this implicit argument. But we can't really do that because, essentially because we don't have coherence. So with coherence, it doesn't matter what scope you go around looking for this show instance, you'll find the same one. Whereas it's important when you have scoped implicit definitions to be clear about whether you're trying to look it up at the definition point. So here, where we're defining print x, whether we're looking there, or whether you want to look at the use points of x of print, whether that's where you want to look. So by providing this parameter explicitly, we're saying that we'd like to look in the use point of print for the instance, rather than look at the definition of print. So yeah, if you miss out the argument here, you just get this ambiguous error because it's not clear what you haven't said what x is. So it could be a float, it could be an int we don't know, and you get an error. So you need that top parameter. So this is just a quick note on the scope of implicits. So
could you explain a little bit more about how that works on the previous slide? So on particularly how the resolution of that sort of show relates to the s and the show in the argument.
All right. Well, you can see at the top that x has been annotated to be s.t, and so and s is available in scope as are show float and show int. But the only one of those that could apply to an s.t, because obviously that's an abstract type at this point, is s. So it finds s trivially and uses that.
Monomorphize print by doing fragmentation, is that solve the ambiguity?
Oh yeah, down here, yeah, you can make this print just work on ints, yeah, and then the ambiguity would go away. So, right. Oh yeah, so a note on an implicit scope. So the only things available, only modules available for selection as an okay, go ahead.
In the slide, you are just show float, then the print will be on float. If I have just one.
If I just used a float there, do you mean?
If you don't define show float and show print again.
Oh right, yeah. If you just said show float, yeah, it would think that it's a float because that's the only thing available. Yes, it would do that. Yep.
Sorry. So
yeah,
the error is just confused. It says ambiguous because show float and show float. But I think you said x is in this context. So aren't neither one of these solutions?
No, in the top one it's abstract because it's s.t. In the bottom one, it's a unification variable. We have no idea what it is yet. So, only things available for selection.
sorry. On the previous slide, if only one instance was available, if only show float was available,
it would select it, yes.
It would select one.
It would select it.
Right, so adding new instances can cause less
yes, but they can cause ambiguity.
Changes in type inference and introduction of ambiguities. Okay.
That makes sense because the function is not yet polymorphic when the type checking it. You have not enforced any polymorphism yet.
Yeah. Yeah, if you wanted to enforce polymorphism, you could do a camel has a syntax for enforcing polymorphism, and then you just get an error. So. Right, so only things available for selection are those which are available directly at the top level. So nested submodules are not available for selection. So in this example, we have a food type and a show food telling us how to show it. But because it's a submodule of n, this print food's not going to work because it can't see it directly. And so you can fix this by opening m to bring it available into the top level scope. And we also have a kind of open implicit m, which just takes the implicit members of m and makes them available in the implicit scope. So that's a little easier. Right, so that's all very good for showing ints and floats, but if I know how to show something of type T, I'd like to be able to describe how to show a list of T's, and the way we do that is with an implicit functor definition. So here I've defined this implicit functor show list, which takes an S argument of module type show, and what it defines is how to show an S.T list, and it has the appropriate definition of show below. And with this in scope as well, we can now show lists of integers. And so essentially what's happening here is it can see that it needs a show with type T equals int list. It looks up, sees the definition of show list, and now it can search for a show with type T equals int, so it finds show int. And then the implicit parameter is filled in with show list applied to show int. And this works on nested things, so we've got this list of floats. Then it also works, and this time it's show list applied to show list applied to show float. That's the implicit parameter to show.
Does this imply backtracking now?
That didn't need backtracking, but it does, and we do have it. Yes.
So if you try out a function...
Yeah, if you try a functor and you can't find a thing, you carry on, you don't consider it ambiguous, which is different from Haskell, where the context is ignored for resolution. So I was just going to talk about some of the errors you can get with searching. So ambiguity, like I said, we're not resolving that when we define the instances, we're resolving it in search time. So if I put these two show ints in scope, which have the same module type, and try and show a number, we get, like I saw on the earlier side, an ambiguous implicit error telling us that there were two possibilities for the implicit parameter. So to help sometimes remedy this, you can explicitly pass your implicit arguments using this syntax, which may help in some situations. And the other kind of error you can get is termination. So here I define an interesting implicit functor which attempts to define how to show things in terms of how to show things, which is obviously not a well-founded definition. So when you attempt to show things after that, you get this error. Now this is a pretty poor error message. We can definitely do better than that. But yeah, the basic idea is you get a termination error. I think it's best to think of these as just another form of ambiguity error, because the problem isn't that we couldn't find how to show an int, it's that we couldn't tell it was the only one. And because of this definition, we couldn't possibly check definitely that there was only one instance. So really termination errors are just another form of ambiguity error. Right, so now onto the things you can do in type classes.
The termination error happens at use time.
At use time, yes, it's at use time. Yeah. I mean, on that particular example, it's obviously stupid. You could probably get a warning, but in general, you can't do it until use time. Yeah, right. So constructor classes are a thing you can do in Haskell and in Scarlet as well. So what they are is where you've got a type class, where the type that it's defined on is a parametric type. So it has a type parameter. So a classic example is monad. We've got the type alpha t in this module type, and the appropriate things for return and bind, which we then lift to be functions that take an implicit monad argument. That symbol is the traditional bind operator in a camel. And yeah, so when we have these defined, we can now define an implicit module monad list, telling you the monadic structure of the list and how to do that. And then we can use bind and return on lists of things, and that all works out correctly. Perhaps more importantly than that, what we can do is we can define functions like when here, which is it's a simple function that if p is true, then it's s. Otherwise, it does nothing. Monad essentially return unit. But the important point about when is it's polymorphic in the monad that it's operating on. So it's polymorphic in m.t. So which is higher kind of polymorphism, which is not something that's normally available in the camel core language. So that's what it is. When would be implicit m monad arrow bool arrow alpha unit m.t arrow unit m.t.
So right, but that looks like an m type.
Yeah, well, but no more so than functors. It's like the arguments that come into implicits are not like just any old module. They're a path, which means that you can use the same type checking for functors that you used for you can use the same type checking here that you use for functors. Once you've got a path, it's much easier to deal with these things.
So that's what I'm getting at. So basically, you have that now on call.
Yeah. Well, you can basically picture them just as functors that have a single return function that's the rest of their thing going on. And it's just a slightly lighter syntax for functors to a certain extent.
Okay, so the implicit argument is actually like the first one, so you can split it into this
Oh no, I don't actually do any of that explicitly. You can put them all over the place. I just meant it's a nice way to think about them. Oh, another thing you get, it's not that important in a camel, we have much better ways to express this already, but it also, it's I think worth just saying this is how they work. It gives you higher rank polymorphism, so that's where you've got a for all that's not at the beginning, you've got a for all on one of your arguments.
If you thought all about the performance story, when you start thinking about your bind, oh wow, I would like my bind.
So, with a camel's infamous inliner, maybe not as good as it should be, but with any reasonable quality of inlining, I think most of these would disappear. In particular, I think functors at the moment just kill the inliner, it just ignores them, so that needs to be fixed.
But the reason I think in some ways it might be worse than functors, in the sense that functors, in principle, you can, functors when used statically, you can defunctorize. There's a relative,
you can essentially do the same thing here. I mean, you're just applying them a lot of times, but you can see. I mean, you can see that most of these they're obviously trivially pure. They don't really do anything, and they're just defining a closure, or they're just defining a function. So yeah, it should not be complicated to. Where's the functor one? Well, it's here somewhere. Doesn't matter.
I think the point is this is less dynamic than ordinary passive different class functions. There, you don't really know what.
Yeah, this is easy. Well, this is easier to analyse than those because, like I say, you get a path, so it's probably. But yeah, basically just a bit of inline, and all of these should be gone by the time that you actually have some code. Where was I? Oh yeah, right. So yeah, so this is having for alls in arguments, and what we've got here with this poly function that takes an f, which is expected to have basically the same type that show had earlier. So this is s.t. And the important thing is that this s.t is, it doesn't have to be the same type in every use case. So we can apply it to ints and we can apply it to floats within the same function. And so that's essentially first-class polymorphism, or a higher rank polymorphism that we're getting from that, which I think is interesting, if not that useful. And it's also, I think, kind of necessary for the way that we do higher-kinded polymorphism as well. So another thing that you can get type classes in Haskell and implicits and Scala is you get associated types, and what this is where you essentially do a search based on one type, and you use that search to find out information about some other types that you can then use. So classic example is you've got a graph, it's got a type T for the graphs, type vertex for the vertices, and type edge for the edges, and then some values for constructing and inspecting these graphs, which we then lift down to be functions of that take an implicit graph parameter. And when we have these, if I were to construct an int graph, which is a graph where the vertices are ints, using some functor that may exist called makeGraph, I could then use from add edge and empty on int like this. And even though we've only constrained the search to say that on the type vertices, we've only said the vertices is int, we haven't said anything about edge or anything about t, it's able to correctly see that x has type int graph.edge list. So that type has essentially come from the search. And that's essentially what associated types give you in Haskell. Right, so status. So we have a working prototype based on the very recently released Camel 4.2. You can install it using OPAM if you know what that is. And you can also try it online, where it's all compiled to JavaScript and some fancy top level. And then when you inevitably find bugs in those things, the code is on GitHub with an issue tracker. So yeah, any more questions?
Do you know how it relates to canonical structures in Coq?
I'm not that familiar with Coq, so I'm not sure, I'm afraid. But ask someone more familiar with it.
And the other one is, how does it relate to the modular type?
So in that case, with modular type classes, they try to stick quite closely to the type class design in terms of being able to detect errors when the instances are introduced, and also in terms of not having to specify that argument when you do a polymorphic thing. And that leads to a few design aspects which I think are a bit undesirable. You have to have they had to have a type named T that was the type they were doing searches on, and they had to have they could only introduce instances at the top level because otherwise the argument thing would be a problem. So it's obviously similar, but I think it's just by using implicits as the model instead of type classes, I think it was a slightly nicer design, basically.
I guess comparison point for this audience as well is the ad hoc polymorphism in F#, for instance, particularly the use of this member constraints to resolve things like addition and subtraction, multiplication, plus there's a separate mechanism for object-oriented ad hoc polymorphism of resolution. But in some ways it's a simpler point in the design space, because it's like simpler but very practical, gives good performance, especially for the arithmetic result functions. So it's worth taking a look.
Probably not as familiar with F# as I should be, so I can't give you any particularly useful comment.
Yeah, it feels like it solves just a lot of the core requirements for ad hoc polymorphism, like addition and show, and so that's just not a problem. It doesn't solve the advanced cases for implicits that implicits kind of cover for monadic programming, for example.
Yeah, really doesn't know, like, it's confused how you're doing this chart, because so you are
This example, or just
how are you doing to do the stuff? Because you have this supposedly an implicit with an so the signature.
yeah.
So you're looking for everything which matches the signature, and then check that it matches the.
So essentially what we do is so when you see the call, you replace all the g.t's or whatever and g.vertex with that one. You replace these. I need to type the signature. Oh well, there's one. So if you're typing F, you basically replace s.t with a unification variable, and you let that run to get the constraints, and then at the point of generalization, you can then kind of fold that constraint that you've learned back into the module type.
But it could even be a type constructor.
So yeah, with the type constructors, yeah, they don't fold in, obviously, because we have no way to represent those in the module language. But yeah, I think the checking is not so much done separately. It's kind of so the stuff in include mod in there. I think there's another one that checks module type then and some constraints against a particular module type.
At the beginning, you provide there's a nice interaction with coherence as per with the module type. But we haven't seen much examples of, for example, applicativity with functionality. So how does that work?
I didn't quite follow the question, sorry.
You told us that module paths were great for checking coherence.
Oh, did I? Well, yes. So coming back a little bit to the discussion thing about coherence, I do think that the module system and applicative functions do give a good way of bringing back coherence for those times when we need it. I think I have one slide. I didn't go, which I wrote during the last talk, so it may be wrong. And I know this doesn't work yet in the current example, but you can see how by having a functor which gives you some generativity, and having that parameter on your sets, you can ensure that you don't use the wrong ordering on maps. So I think that's an interesting way to look at it. But it's probably, yeah, like I said, more of a design package. So I don't know that that's what you.
Maybe I missed it, but what is the story about if you got special case like the type name T or some kind of type on which you're doing dispatch, how do you compute the implicit?
Sorry, do you have a specific example?
Well, I don't know, all your examples you use type T, so in that way it looked very similar to type T. But you're saying it's more general.
Yeah.
So
how do you know which type? You're doing it on any information that you have available. So, for instance, when I did so here we don't know anything about type T when we're doing this. All these from and edits. What we know about is type vertex, and we've left type T and type edge or kind of abstract, essentially like existential in the search. So you do the search on whatever information you have available to you.
Okay.
Yeah.
Yeah. I mean, but I guess so. Like in the modular type classes, you wouldn't be able to do this, and that was kind of deliberate because you actually might have various graph implementations that all have vertices as integers.
Yeah, you could do, but then all you need to do is a little type annotation saying which one you meant, and the ambiguity goes away. So.
When you do a resolution, you refer to all type integers, that's how you can know.
Yeah, so we do it at the point. So when you have a variable that's come out of removing one of those s.t's, it's at the point where that variable will be generalized. You do the search.
So your functions can you do the search in two senses combined. For instance, you have two variables you find, and just one choice. If you want to solve both of them,
No, yes. So the searching is done in a specific order, and you can't rely on results from later searches for earlier ones. So it's kind of a principality of it. Like if you're using your first argument search to constrain your second argument, that's fine. But you can't. Yeah, it won't try and find a match, because then that's just non-terminating. You can quite easily express it all that's 10th in here if you start allowing backtracking across these kind of. Yeah, well, personally, I would have those be non-principal, and I mean, because you can always fix these things with some type annotations when yeah. So.
I have one question: how costly is it to actually?
So it's hard to say. I mean, I think technically it's going to be polynomial, but that's not a particularly useful measure. So I think that there will be pathological cases that you can make it take a long time, but I suspect that for the kind of things.
Well, it's non-terminating.
No, it detects the non-termination, so it doesn't. There's no chance of this being just running forever for you. So the recursion has to be well structured. It's got to be on a smaller time, basically. So, yeah. So I suspect that the kind of code you will write, if you use it for what it's designed for, ad hoc polymorphism, I think there's no real problem with the search being too large. If you try and abuse it, like people like to abuse type classes sometimes, perhaps the compilation times would increase. So it's hard to say. We only recently have the prototype. We haven't got enough code using it to really say. So.
Okay. I think we're already eating like 10 minutes into the break. We have a little bit of time after the last talk this afternoon, and we might actually extend this discussion because there seems to be a lot of interest in this topic till after that. So if people are interested, stay here after the last talk, and we can have like an extra offline kind of ad hoc panel about this.